Okay, we are in section 6.3 for MAC 1114, continuing with page 3 of the theorem outline. And at the very top of that page, it says you are now ready for problems 1 through 3 in the homework outline. So if we look at those problems, it says, what is the domain of the tangent function? So you can just look back at where that graph was presented. The domain, as we stated, let's look at that together again. All right, so this is what you're looking at to answer that question, one of the graphs that we just went over. So what's the domain? All real numbers except odd integer multiples of pi over 2, as shown by the asymptotes and stated up here at the top. So let's see, what can we look for here? Okay, so let's see. All real numbers except odd integer multiples of pi over 2. So that would be E. Okay, you're not doing a problem. You're just looking at the graph showing you understood what was discussed in that section regarding the tangent graph. Number 2, which of the following is not part of the range for the sine function? Remember that the sine function, let's look at it again. The sine function goes as high as 1 and as low as -1. That's your range, in between 1 and -1. So what's not included in that? 1.5. If you want to try these other numbers, that is in between those two numbers. This is in between those two numbers. Or they said which is, look at the way they put it, which of the following is not part of the range. That is part of it. That is part of it. And you can put, if you didn't know what pi divided by 4 is, you could always put that value in your calculator. So you could just go second function pi divided by 4. See, you get 0.78. That's definitely between -1 and 1. But, first answer was a giveaway. It's too big. It only goes as high as +1. So that's too big. Part 3, number 3. For what numbers is the function called tan of theta not defined? So they were saying where the asymptotes are, which are odd multiples of pi over 2. It's not defined for odd integer multiples. That would be what goes right in there. Multiples of pi over 2. Okay, same question they asked in number 1. Okay, getting ready for number 4. Let's continue with our theorem sheet. We were already on page 3 of the theorem sheet, and we have completed 1 through 3. So next one, a function is called periodic. So this is just what I was discussing when I introduced this section, that as you revolve around the circle repeatedly, you're going to have the same stopping positions many times. And so you'll get the same value for cosine or sine or tan as you rotate repeatedly. And that's what, this is just an algebraic way of stating that. I was trying to explain it to you in a way that you would understand a little bit better. Okay, so, and how often the values repeat, that's known as the period. How long does it take before the values start repeating is what we call a period. That's a definition of a period, and I'm going to explain that even further when we go to do the graphs. I'll be able to show you a picture of the period. So what you're seeing here is they're trying to point out to you how often, but they're trying to point it out algebraically. I'm going to point it out 2 different ways to you. Is in these definitions right here, see how they're saying theta plus 2 pi? That means that the period, this is how often, every 2 pi units, your answers for sine, the sine values, they're going to repeat every 2 pi units, every time you revolve around the circle 2 pi. So the period for sine, cosine. Let me just abbreviate them. Secant and cosecant, because they're related to sine and cosine. Let me just write this like this. So for sine, cosine, secant, and cosecant. Oops, wrote that wrong. The period is 2 pi. And that's what they're trying to show you here with this 2 pi here, 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 and here. For tangent and cotangent, they have a different period. So for tan and cotan, the period is 1 pi. Okay, which is stated right here. That's what they're trying to say to you algebraically. So you can expect that every time you rotate around the circle 2 pi, the answers are going to start repeating. Okay, now I have an example here. Determine the period of the sine and cosine function. The angle associated with the given point is pi over 3. What is the period of the cosine function? But you already have that. So what we're saying here is that whatever the value for sine is at pi over 3, if you just add 2 pi to that, you're going to land right back on the pi over 3 location. And at pi over 3, look at what your central angle is. When you rotate pi over 3 units up in the air, pi over 3, let me remind you of what you did in 6.1 and 6.2, converting radians to degrees. This is 180. 180 divided by 3 is 60 degrees. So you're talking about a 60-degree angle right in here. So if you were to drop this down to the x-axis, this y-coordinate would be the long leg, and therefore is square root of 3 over 2. That's why that is there. And the 30-degree angle would be right here, which would make this the short leg and make it 1/2, which is where they got that. So a review of what you did in section 6.2, but we can drag it into this conversation. So when you're at a point that is 60 degrees up in the air, a rotation of 60 degrees has happened in order for this terminal side to stop right here. This rotation of 60 degrees is equivalent to the central angle. It is also the angle right there. That makes that 30. Therefore, you have a short leg and a long leg. So what the discussion about being periodic is this. If I'm at pi over 3, I've rotated pi over 3 degrees, or what we call 60 degrees, and then I went an extra 2 pi, I would land right there again. When you rotate a full revolution or 2 pi, you land right back where you started from. So I'd be right back here again and end up getting these same values again. And that's what we mean by the periodic nature of a trig function, where the values repeat. For sine and cosine, those that amount, that distance that you have to move in order for values to start repeating is 2 pi, and we refer to that as the period. Okay, so maybe you want to memorize that, as I would try to memorize the ones that stick out from sine, cosine, secant, and cosecant, which are the tan and cotan functions. They are the only two that have a period of 1 pi, and then their answers start to repeat. And for all the rest of them, it's 2 pi. Okay, we also have what's called the even and the odd properties. And before we go on, let me check the bottom of this page to see if we could have gone on. Yes, we actually could have gone on to problem number 4. Let's do that first. So doing problem number 4 from the homework outline. It says sine, cosine, tangent have a period of 2 pi. So this whole page is just, you're not doing any problems. You were just looking at the graphs and the information that was given with the graphs and the demonstrations to try and explain those things and just kind of filling in the blanks. So these are the ones that all have a period of 2 pi. And then tan and cotan, as I pointed out, are the odd ones that have a different period. They have a 1 pi period. Okay. My math lab repeats the question twice, so it's the same two answers to fill in there. Okay, back to the theorem sheet where I was beginning to talk about odd and even functions. I'll try to relate this to something you learned algebraically. When you were in an algebra class, you would learn that this is an even function because it has an even power, like in the picture, that's a parabola. And this is an odd function. So, and they would start it off like this, giving it to you in function notation. So the essence of an even function, whether it's algebraic or trigonometric, is that when you plug in a negative value right here for any even function, and then this would be an odd function. So for any even function, when you plug in a negative right here, regardless of the negative that you're plugging in, it doesn't affect the function at all. In fact, you get the same value that you started with, even if you were to put in a positive. So whether you put in a positive or a negative, the negative goes away and it remains unchanged. And I can show you this actually even better with plugging in a negative variable. Let's do that. So look, if you were to plug in negative x here rather than x, would that change what you get over here? So you would plug in the negative x, do what the function says, and still you come right back to the original function. So that's the essence of an even function, that even plugging in a negative, the negative goes away and you get right back to the original. And that's what they're trying to say with this and this. These two that you see right here in the center are called even functions. Cosine and secant. See how when you plug in a negative, you get the original back again? When you do secant of a negative value, it's the same thing as doing secant of a positive value. So what we're saying is that you can disregard the negative when you're doing evaluation problems where you're plugging something in here and then trying to give me the value. You can, if I give you negative 60 degrees, you can treat it as though it's cosine of positive 60 degrees. All the rest of these are odd functions. See, odd functions, when you plug in a negative, it doesn't go away. Let's try plugging in a negative x, both in the function name as well as the function that shows the operation. So if you put a negative x in here, that would be negative x times negative x times negative x. You would have a negative left over. So the function actually does change. It started off as positive x cubed, and that negative had an impact on it. So that is the characteristic of an odd function, that a negative impacts it, whereas for an even function, the negative does not impact it. You plug it in, you end up with the same original function. And that is what you're seeing here. These are all odd. These two are odd functions, and these two are odd functions. So again, you want to memorize all 6 of them in the most efficient way. Memorize the ones that stand out. And that is cosine and secant. Those are considered the even. Those are the even functions and have all the characteristics of an even function, which is that the negative does not impact the value. Okay, we can now do numbers 5 and 6, although we're going to probably run out of time. Let me see on this video anyway, because these are just 15-minute videos. So let's see. So for number 5, it says f of x is equal to negative for all values in the domain. Okay, so when you can plug in a negative and it's equal to the original, that means that it is an even function. Okay, I'll pick up with these concepts in the next video.